My name is Thuong Phúc, and on behalf of my collaborators, today I would like to talk about the topics of how to probe the single particle properties of nuclei using the proton-induced nucleon knockout reactions of the PPN type. So here is some of my collaborators who I work with. I will present our works in this talk. So the outline of my talk today will mainly focus on two topics. Most of my talk will be on the topic of quenching of spectroscopic factors using the PPN reactions and analyze the data as GSI. And then I will spend some time talking about my latest research on the molecular orbital study using the PPN reactions on beryllium-9. Okay, so I would like to spend a slightly longer than usual introductions on this topic of the quenchings of spectroscopic factor. So the spectroscopic factor is, you can roughly interpret it as the amount of the overlap between the pure single particle pictures and nucleus in realities. So what was found by Labicas in 1993 using the EE-Prampi like electron-induced nucleon reactions at NICHAF, Netherlands, which is considered one of the cleanest or best probe for this kind of spectroscopic factor study. And what he found is that for the stable nucleus here, the spectroscopic factor is usually quenched to around 60 to 70% due to some short range and long range correlations. So usually these days, in terms of experimentally study, we one of the most commonly used quantity is the reduction factors defined here as the ratios between the experimental cross-sections and the theoretical cross-sections. So before I proceed further, I would like to try to avoid possibly confusions for the later slides. So some nomenclatures that we use in our work is that we use the word nucleon removal for, like, example, these kind of reactions, a beam and in inverse kinematic is impinging on the barium-9 target or the carbon-12 target, which sometimes people usually refer them as like heavy ion knockout or sometimes breakup reactions. But in my talk, I will refer them as nucleon removal process. And then I will reserve the word knockout for the PPN and EE-Prampi reactions, which themselves also sometimes referred to as like quasi-free scattering. So using these nomenclatures, I proceed to the main topics today. So this is a very famous plot to illustrate how the home problems. So on the y-axis, we will have the reduction factor defined as the like in my previous slide, and then on the x-axis, you will have the what we call the proton-neutron asymmetries, defined as the difference between the separation energies of the knockout nucleons and the other type of nucleons. So in this talk, we call them like delta S. So the more positive, the larger positive value that you got, you will have the strongly bound knockout nucleons. And the more negative value you will have the weakly bound knockout nucleons. So what they found using the several MSU groups found using the nucleon removal reactions is that there is clearly observed trends, which is with the slope is very steep on the reduction factor as a function of delta S. Or in another term, we can say that the reduction factor is strongly dependent on delta S. So, and this plot has been reanalyzed in 2014, and the data is very consistently show about the step of the slope. So what is interesting is that using transfer reactions. So transfer reactions is traditionally one of the most common tools to study to obtain the spectroscopic factor from experimental data. And these those study I show here Also, like in MSU, show that if you're using transfer reactions, usually you cannot observe any strong dependence of the reduction factor on the delta S on the proton-neutron asymmetries. And there has been a lot of study using transfer reactions, and they always show that no strong delta S dependent is observed. And in my opinion, the more data that they analyze, you can see that it's not even like doesn't have any clear trend at all. The data is just uniformly is distribute on this strength. So I think that this week, later on this week, Juan Manfredi talk will also present the latest study of the MSU group, and based on his abstract, I think that the conclusion is still remain the same. Even with the high nuclear energies, there's still no strong delta S dependent is observed. So some people argue that probably because there is a difference between the definitions of reduction factors between transfer reactions and nucleon removal reactions. However, several other studies made by the Bayhan groups and also by Ben K et al. As using slightly different definitions for reduction factor also doesn't observe any strong dependence compared to the nucleon removal resource. So that is in terms of the experimental probe. For the microscopic structures calculations, people also, the result is not very conclusive in my opinion. So they did found that the quenching is due to short range correlations and also long range correlations, several types of studies, and these are the ab initio calculations, curve cluster and SCGF, the cell consistent green functions. Andrea Idini did several weeks ago, it mentioned several ingredients for this. So what they found is they observed some trends of the quenchings, but it's not very clear. And usually when you look at these pictures here by the curve cluster calculations, it may seem like a very steep slope, but if you replot it with the appropriate y-axis scale, I will show you later in my talk, you don't find it very strongly dependent at all. Another very interesting line of work is the dispersive optical model analysis, which is very interesting in my opinions. So they calculation, they parameterize the potentials based on the Maho-Soto dispersive relations, and by fitting with several observable, they can get some structure information. For this case, the spectroscopic factors. And when I replot the data in their work, there's also a slightly weak delta S dependence. So the picture is not that very decisive. So why this topic of the difference between nucleon removal resource and transfer reactions resource is important, and why should we care about the slope of the reduction factors? So in terms of nuclear structures and interactions, it may tell you how well does the single particle pictures is valid, and some informations on the hardcore, repulsive hardcore, or the tensor part, the high momentum part, and some emergence effects of exotic nuclei when you go very proton rich or very neutron rich. But in this case, for nuclear reaction, is have a very important impact, because both the nucleon removal and the transfer reactions has been used a lot to extract spectroscopic factor for a lot of study using them. And the results that I previously showed, that it's very clear that one of them is fundamentally has some problem with the capabilities to extract the spectroscopic factors. So it will affect a lot of study. So for those study on the nucleon removal and transfer reactions, you can see the talks by Bonacoso, Timofeyuk, and Manfredi in previous week. So I will try to investigate the biggest questions here is the slope as a function of delta S. So the solution that our groups and several other groups pursued is to investigate another third kind of reactions. So in this case, is the proton-induced nucleon knockout reactions, PPN. So I should state that at this moment there is like 4 commonly used theoretical models to investigate the proton-induced nuclear knockout reactions in inverse kinematics. So the most well established and also the one that has been developed the earliest is the partial wave distorted wave input approximations, or DWIA. So this is the model that our groups focus on. And then we also have another variation of this is the Iconon DWI, which use the Iconon approximations for the distorted scattering wave. Then there is the transfer to the continuum in CDCC framework by the 7 groups. So I should note that this is not the transfer to the continuums model in the semi-classical Bath integral of Angela Bonacosos, but this is basically CDCC in prior forms. So, and Mario has a talk in his first talk in the seminar series here. And last but not least is the 3 bodies Faddeev equations in Angras and Sanhas form by the Lisbon groups. So here is some of the very first resource of the proton-induced nuclear knockout reactions on the inverse kinematic measurements with the radioactive beam, which has been measured at this moment is at 2 facilities. First is the R3B LAN setup at GSI, and the other is the RIKEN RCNB collaborations in Japan. So for these 2, you can of this study state that there is no strong data as dependent observed either. So all of the published data, I cite them here. So as the GSI R3B LAN data, I should also note that 3 out of 4 models I presented earlier has been used. So one of the goal of our work is also try to use the partial wave DWI, the longest developed models for this data as well. Another interesting, very recently works is using some of the early P2P data by the GSI works and several EEPRAM data. Pastoralists and also perform a phenomenological study fitting these data and try to get some empirical study about the quenching factors. So then if what is the problems that our groups try to solve in this work is that the extract spectroscopic factor and the reductions factors is strongly depends on the reaction model. Is not an observable. So we try to answer the question that how much does the choice of potentials, optical potentials, and the bound state potentials corrections used in the reaction model affect our resource. And the current reaction model, they include all necessary contributions to accurately extract the spectroscopic factor. So in another case, we just try to validate how reliable does like standard model, especially focus on DWIA, that can extract the reduction factors. So this is a very nice illustrations provided by me by Ogata-san. So this is the a nice mechanisms of how the proton-induced nuclear reactions works. So as you see here, this is protons which interact with the valence nucleons, and then based on the kind of like the free scatterings, it's knock that nucleon out. So the whole process is just similar to the way that 2 nucleons are free scatterings, but in this case it is inside the nucleus medium. So that's why sometimes people refer them as like quasi-free scatterings. in our work, we only use the word quasi-free conditions for like the recoil momentums nearly zero or the regions near that, or for those words. So in terms of the transitions amplitude of the distorted wave input approximations, it is can be nicely represented using this formula, and there is only 5 ingredients required. So 3 of them are the two-body scattering distorted wave functions, and then this is a bound state wave function of the valence nucleon, the single particle wave functions, and then this is the two-body nucleon scattering matrix. And if you use some form of approximations, you can even factorize this two-body nucleon scattering amplitude as experimental measures cross sections. So that is one of the strengths of the DWIA is it's flexible, and you can easily account for several kind of corrections. So I should mention that in normal kinematics, the partial wave DWIA that we use is a very well established method, and it has been long used to study these kind of spectroscopic factors. As a review papers in 2017, here show that the spectroscopic factors of the P2B using DWIA versus the one by E prime P has a like very good agreements, and it can very well describe the data in the quasi-free conditions. So now we will use this model for the inverse kinematic data. So we analyze at the moment of this work, we analyze the 18 available reaction data with the beam energies from 300 to 450 MeV measured by the R3B lens setup as GSI. So here's are the 18 case, and our input with some uncertainty accounts. We're using, for the T matrix, we're using the one by Franilov, and for the scattering wave functions, we use the EDAD to Dirac optical potentials with 10% of uncertainty. We evaluate this uncertainty by using different versions of the Dirac optical potentials. And then for the bound state wave function, we use the prescriptions by similar to the one by Cheney. So we constrain the radius, the root mean square radius of the single particle wave function with the one by Hartree-Fox SKX interactions with 10% uncertainties. And this is a very important ingredient is the non-locality corrections. So we use the Berry factors for the bound wave functions and the Darwin factor for the scattering wave functions. I will mention about this factor later in this talk. So the last ingredients is the theoretical spectroscopic factors. So we use the one calculated by standard configuration shell models with WBT interactions, and these are provided to me by Marios and Matthias. So essentially our work and the one by Mario and Moros and Antonio, and also the one by Matthias Horn, we literally using the same spectroscopic factors for these data. So this is the first resource. The red dot here is our DWIA calculations using these simple formulas. We take the experimental cross sections and then divide by the theoretical spectroscopic factor multiplied by the single particle cross section of given by the partial wave DWIA models. So one can immediately see that the reduction factor are very weakly dependent on delta S. So it is in good agreement with the transfer reaction and also in others like protons in the nuclear knockout reaction study, and it is not in agreement at all with nucleon removal study. Another thing that you can see is actually our value, the magnitude of the reduction factor is very large compared to what have been found in the EEPROM P study. So they found a quenching of around like 0.7, 0.6, but this one is like nearly no quenching at all. So in the later part of my talk, I will try to analyze and to answer why this magnitude is too large. So now for the order like the green, the blue, and the black dots. So this is using the ab initio structure calculations. So SUGF and group cluster using several kind of chiral interactions. And you see that if you replot them with like this y-axis scale, and also you using the experimental data for the separation energies, you can see that they are also kind of weakly dependent on the delta S, and the slope is like by no means a very steep slope like the nucleon removal. So now for another part, we compared with all the reactions model, the three of the rest reaction model. So one can see first, to compare with the TC model by Mario and Antonio, you can clearly see that although the two models actually quite different in our choice of the potentials and corrections, but the slope is like basically parallel to each other's, which is actually a good signal. That means that no matter what magnitudes that you get, you still got like no very weak dependence on delta S. And then we also, this slope is also in good agreement with the icon on DWIA. For the FADEF is because it's lack of, mostly because of the relativistic corrections. So the magnitude of it is quite lower than the rest. So then we know now for sure that the slope of the models are very like in good agreements with each other. Then why is the magnitudes of the trends are different? So what caused this difference? And then this is the work by my Japanese colleague and in collaboration with the Sabin groups. So what they found is that essentially if you're using identical choice of input and corrections in DWIA, in the TC, and in the FADEF, then the results should be the same. But because in practical analysis, there are several papers of us, and then if each of our analysis, we use slightly different choice of inputs and corrections. So that will have some impact on the reduction factors. First is the lack of molar factors. So like some of the model, they did not properly include the molar factors. And this will have, this factor is like, it exists because as a relativistic boost from the two bodies, nucleon center of mass frame to the nucleon nucleus center of mass frame. So if you do not include these molar factors properly, you may have an impact of up to nearly 28% in terms of the reduction factors. And the higher the energies you go, and the more the impacts you will get. So another important factors is in some model, because it is technically difficult to implement the energies dependent optical potentials. So they choose the energy independent potentials chosen at the half the energies of the incoming protons. So it also has some slight impact, up to 10% of impact in some case, depending on the separation energies. But more crucial is the non-locality corrections. Yeah. So this non-locality correction has been like discussed very extensively by Natalia on several weeks ago, also on this reaction seminar. So for the proton-induced nuclear reaction for DWIA, we simply just need to multiply them by the corresponding barrier factors and the dark wind factors to account for these non-locality corrections. But we found that if you do not account for them, the impact could be almost like 25% in some case for like strongly bound case. So last but not least is a new effect that it's not like new, but like the effect that usually not very well discussed. So we found that the two data here, the red is the one we do in our work, and the black is the one analyzed by Kawase-san at RICAN RCNB. So these two basically use identical theoretical framework, the partial way DWIA, and all of the joys of the like non-locality corrections and potentials are very similar to each other. But you can see that the one measures at RICAN RCNB collaboration is slightly lower in terms of magnitudes compared to our resource. So what is the difference between the experimental setup at RICAN RCNB and the one at GSI is that the one at RICAN RCNB, they implement a very strict kinematics. I mean, the experimental acceptance in terms of energy acceptance or angular acceptance to ensure that what they measure is just around the quasi-free conditions compared to those as GSI or RGB land. They basically they measures of the event possibly events. So we think that some contributions may appear in the GSI RGB land data, like higher order effects like concitations or like probably charge exchange effects are possibly missed when you use DWIA type calculations to analyze these data without putting any experimental restrictions on it. So to illustrate this point, let's see, this is transversal momentum distributions measures as GSI, and the solid black line is our calculations, and you can see that it does not agree where it's underestimate the experimental data in these regions around more than 140 MeV on C. And basically this shape is we share is that's very similar to the one using TC and the one using FADEF calculations. They also have some slight underestimate of the data here. But if you don't use any like no locality corrections, and then you will get like what we call a wider shape for it. And in some sense, the lack of probably no-locality corrections may hinder the real effects, and it may mask, as it cancel out the real effect, and you don't like really see the problems. So, and so to sum up on the missing contributions, I should mention that DWIA in terms of normal kinematics works very well because they were performed using, in terms of normal kinematics, they always perform around the quasi-free conditions. Why some of the data measures like as GSI, we using inverse kinematic, but we are using, we are implement any restrictions, you will see that there's a lot of underestimate at higher recoil momentums. And these agreements, basically when you, for normal kinematics, you just fit at the peak, right? So, but for the, this kind of semi-inclusive reaction, we usually integrate out to get the integrate cross-sections, and then we divide, we get it divided by the experimentally cross-sections. So all of the discrepancy you see here, it will get accumulate, and then it will result in some discrepancy. Basically not accurate extraction of reduction factors. So to summarize this part one, so what we found is that the reductions factors extract from PPN reactions, no matter which model that you use, basically they all have weak dependence on the proton-neutron asymmetry data S. So this is completely in good agreement with transfer reactions, and disagree with nucleon removal data. Another thing is that we would like to emphasize the importance of the non-locality corrections, molar factors, and also the use of a proper energies dependence in a design energy range. for the optical potentials, because if you don't probably include them, they may have non-negligible impacts on the PPN cross sections. And last but not least, we think it is very important to pay some attentions and to have some more study on higher order contributions effects in inverse kinematic when you don't have any kinematical restriction tech in the experiments. So this one was published last year in PRC. So for part two, before I start part two, I would like to say that in like the last 5 years, there has been a renaissance of proton-induced nuclear knockout reaction study. And that's, I think, probably due to one of the main driving factor is due to the C-star collaborations, which use the PPN reactions to study the spectroscopic informations of exotic medium mass nuclei. And there are also several other studies using the kind of like PPX in general. There is the Borromean structure study with TC, run by the Sevin groups, and also Kikuchi-san and Japan's. For the tensor correlations, there are also a study using the deuteron knockout reactions. And for the short range correlation, this is a very interesting part, but it's not very well studied at this moment. So there is a few studies. Very recently, so Foster et al. Has published papers on the B2B sequential knockout at the recent data experiments. So as my Japanese college groups, there has been several alpha clustering study using PP alpha reactions with DWI and the microscopic THS AMD models. Have been several works done at RCNB, and also several weeks ago, like Zai-Hong Yang has also have a talk on the study using PP alpha for several other exotic nuclei. So what I want to present in this last part is that we try to study the neutrons molecular orbitons using the neutrons knockout reactions with the combinations of DWI and DHS AMD wave functions. So the neutron molecular orbiton is basically similar to, this is a nuclear analog to the molecular orbiton we found in molecular physics. So what we found is several cluster structures as demonstrated using the extend Ikeda diagrams here. When you put neutrons on top of them, that neutrons will behave in a certain way and will have a certain orbit configurations, like the p-type orbits, for example, or p-type orbits. So this one has been reviewed by Fornessen, but we focus on that to this point, there is no experimental proof for the radial wave function of that valence nucleons. All of these work, they mostly study the properties of the energy level scheme, for example. So now we try to put some physics into this model by focus on the overlap, what we call the overlap functions in the transition amplitude of a standard DWIA amplitude. So this overlap function, sometimes we also refer it as the bound state or single particle wave functions. So there are actually too many options to calculate these overlap functions. The first is like you using a Wu-Saxon potentials constrained by Hartree-Fock calculation, which is the one that I used in my first part of the studies. And then you can use the Wu-Saxon obtained by EBRAM study. You can have some like system approach. More recently, we have the non-local dispersive optical models, or you can directly calculate them by ab initio model, which also has been done a lot for neutron removal transfer reaction, and some of the later very recent work using DMC, for example. Or you can also use other, like, to a lesser extent, the just correlations method. So in this work, we used what called the reduce with amplitude. Basically, we put it to this is the overlap functions in this sense. This is given by the antisymmetry molecular dynamics, the AMD, and the THSR, the Tosaki Horiji Shukrup wave functions. So here, I will show you on the left hand side, you will have the valence neutron amplitude. This is also the reduced width amplitude plot. And on the right hand side, you have the valence neutron distributions from the two models, THSR and AMD. The main difference, the main physical pictures different in these two models we use in our calculations is that by THSR, they put a very certain configurations for the valence neutron and to alpha clustering core of barium 8. The AMD calculation, it allows you to have some cluster breaking components, and it allows you to degenerate the wave function of the mixing of these different configurations. So well, what we found is that if you just using the PPN reaction with barium 9 with DWIA, you can clearly see a very clear distinctions in terms of magnitudes when you're looking at the TDX cross-section. And this TDX, of course, we try to get it in the quasi-free conditions, as I mentioned before. It is actually not a very big problem if you perform the calculations, perform the experiment in terms of normal kinematics. So we can clearly see, although there is some uncertainty if using a different potential like Fonding potential or Dirac potentials, you can still clearly see the difference in terms of the pictures. And that we propose that using these kind of reactions, we can determine which is the more appropriate or realistic pictures of neutron molecular orbitons. So this is the end of my talk. So thank you for your attention. Okay.
Okay, so can you hear me?
Yeah.
Okay,